Okay, welcome to my screencast on electricity. I just want to let you know this is my first time doing a screencast, so if it doesn't all turn out perfectly, please be forgiving as I am figuring this out. Um, let's just do a real quick review. Last time in class we were together, we learned a little bit about ions, and we said ions are atoms that have an overall negative or positive charge, like this atom up here. It's got 2 protons, 3 electrons. Those electrons are negative, therefore it's got an overall negative charge. The ions cannot move through a solid, but they can move through a liquid, which is why batteries are mostly liquid. And that's what allows batteries to work. It's the electrons that actually move around in an atom. The electrons can move from atom to atom, and therefore they are the things that can create a negative charge. We also talked about insulators and conductors. We watched a video um, where someone had a conductor all around them and the electricity could flow around their body, not through them. Insulators would be plastic, wood, skin, rubber, things like that. We said there's an electric force. That's the attractive force or the repelling force. Remember, opposites attract. That's a Paula Abdul song. And the likes repel from each other. We also said that if using something like a Van de Graaff generator, which you can see down here in the corner, this girl has negative charges all through her hair. Therefore, those negative charges repel each other, and each hair repels from itself. There is an electric field that's generated um, as electricity flows through something. So these tools down here, they don't actually have to tap into the wire itself. They simply measure the electric field, and they can measure the strength of the current running through those wires. And then we talked about induced charges, which is kind of like a fake reason for having a charge. We rubbed a balloon on someone's hair. We talked about St. Elmo's fire. That's not on your test, but that's another good example of an induced charge. And then we also talked about electric discharge, which is a whole bunch of electricity striking all at once. So that brings us up to grounding. Um, and grounding is providing a pathway for excess electrical charge to flow into the earth. Now, this can be an electric impulse like lightning, or this could be extra electric current. But in this case, if you look at most sockets, you'll see that it's got a neutral, which is the larger prong. It's also got the hot, but it's also got a neutral, or I'm sorry, not a neutral, a ground. And the ground is what takes any extra electricity. If for some reason there is a short in the device you're using, maybe it's a vacuum cleaner or a hair dryer or something like that. If there was a short, it would actually send that extra electricity through that ground. And most people have this tied to their electrical box outside. The electrical box would be right above here. And this is usually a 6 or an 8 foot um, copper peg, I guess you could say. And here it's only sticking a few inches out of the ground. And if there is extra electricity, it flows into the earth. Same thing with this. This is a lightning rod on top of a house. If lightning were to strike near the chimney, it would most likely strike the lightning rod. It would travel down this lightning rod down the side of the house and into the earth. Um, for this reason, it's the earth that can accept large amounts of excess charge because it's so massive. If it were smaller, it could not accept all this amount of charge. And when I mean smaller, I mean like, the size of a large basketball or the size of a football field or something like that. But since our Earth is so massive, it can accept all this electrical charge. And the houses often ground their electrical outlets to metal pipes. So the pipes that run out of your house, if they're metal, sometimes the ground wire goes to that, and then the electricity passes through those metal pipes into the earth because the metal pipes are dug into the ground outside. And that way the electricity flows into the earth. So here's a question. Why is it a bad idea to take a bath or shower during a thunderstorm? Well, if you are taking a bath or a shower and lightning is striking around your house, it doesn't necessarily have to strike your house exactly, if it strikes the pipes that are buried in the ground, there could be some extra electricity to travel up those pipes, which carry the water, and therefore, if you are covered in water, that electricity will actually flow to you. So it's probably just a bad idea during a lightning storm to take a bath or a shower. Let's keep going. So we talked about electric discharge. Now we're talking about electric current. Electric current is the steady continuous flow of electricity. Unlike electric discharge, which is a short burst of electricity. So electric current is a continuous flow over a long period of time. Um, the electric current will only flow through an electric circuit. So probably one of the best ways for us to imagine this is to look up here at this diagram. You can see that we've got water flowing, and this water is flowing in a closed circuit. So the water is being pumped up, and once it's pumped up, now it's got some gravitational potential energy. It starts to fall down. And as it falls down again, it can go back to this pump and go back up. But my question is, let's just suppose this was broken. If there is a trap door allowing all this water to flow out, would this system work? It wouldn't. So in this case, an electric current can only go through a closed circuit. If the circuit is open in any way, shape, or form, the electricity cannot flow through it. So electricity behaves much like water in a closed system. We've got some videos in the future to show you how the electricity does flow a little bit like water in a closed system. And take a look here. We've got the electrons flowing from the negative part of the battery. We'll talk more about that here. Going to the load, which would be the light bulb, and then back to the positive side of the battery. Notice the electricity only flows when the current, or when the circuit, is closed. If the circuit is open, there will be no electricity that flows. So in this case, this is a current, and the current has to go through a closed circuit. Okay, let's look at some more of this. A circuit, by the way, is a closed conducting loop. So this is a circuit board in the upper left-hand corner, and you can see it's got all sorts of wires kind of soldered in there, and it goes to some computer chips. Probably the best diagram to help us understand how a closed circuit works is this one down here with the battery. The current is only able to flow through a closed system. We covered that. But here's the question. Why do the electrons flow from the negative terminal to the positive terminal? So look at this. We've got electrons, which are the blue dots. They're flowing away from the negative terminal through the wire, and they're flowing to the positive terminal. Why are they flowing in that direction? Well, if you think about it, remember, opposites attract, like things repel. If we have like things over here, we've got negative electrons on this side of the battery, and we've got negative electrons in the wire. Where do the negative want to go? Well, they're not attracted to each other, so that means they're actually repelled by each other. So these electrons say, ew, other electrons, I'm getting out of here. So they get away from this negativity as much as they can. But they know that there's light at the end of the tunnel, because remember, opposites attract. So we've got these negative electrons, and they are so very attracted to these positive protons. That's all they can really think about, is going towards these positive protons. So because this battery's got a positive side and a negative side, that's what allows the electricity to flow. And that's really all batteries are, is a positive side and a negative side. Now notice this diagram over here actually has it backwards. It's got the electrons flowing from the positive side. That's incorrect. In fact, they would go from this side and they would go backwards. Okay, so I suppose the next question is, how do we measure this flow of electricity? Well, first off, there's amps. Amps is the unit given to the measurement of the rate of electric flow. So it all depends on how fast something is flowing. So the greater the electric flow, the greater the amperage. Well, let's look at this real quick. I think there's a question that goes along with this. Which of these has the greatest amperage? This is not a trick question. Here, the fire hydrant, of course. The fire hydrant has a lots and lots of flow. There's water flowing out of this like crazy. I mean, there's gallons and gallons and gallons. But take a look at this hose. It has less flow. And since we can model electricity by using water, in this case, we would say that this fire hydrant has greater amperage. This hose down here has less amperage. Well, whenever we talk about the amount of electricity flowing through a circuit, that is the amperage. Take a look at this battery. This battery is only 12 volts. However, it's got 850 cold cranking amps. That means it's got a large flow of electricity. That's what your car needs on cold days. Your car needs a large flow of electricity. Now, a normal battery like a hearing aid battery or a regular AAA battery is not going to have that kind of amperage. Just because no devices need that kind of amperage except cars and engines to get things started. They need a lot of amperage to get started. So vehicle batteries are often classified by how many amps they can output. Next, voltage. Voltage is the measure of the amount of electrical potential energy. So in this case, take a look at this battery. We've got 1.5 volts, and in this case, we have 12 volts. Now, when we think of electrical potential energy, the key word here is potential. It has the ability to do something. That doesn't mean it's doing anything yet, but it has the ability to do something. There's a video that I'm not going to show you right now. I'm going to have you pause the video in just a second, and then I'll provide a link for you on YouTube in order to follow this. The reason why we're not going to show it together right now is because I have a limited amount of time when using the screencast software, so I have to fit all my information into a certain amount of time. So we're not going to watch the video together, but this will explain amperage as well as voltage. Now think about it this way. This has got a lot more chemicals in it, right? And since it has a lot more chemicals, it's got a lot more potential to do some electrical stuff. This one has a lot less chemicals in it. Therefore, it has a lot less potential to do electrical stuff. And the voltage is the amount of potential electric energy. In the video, I model it using water. Think of it as the amount of water flowing out of a cup versus the amount of water flowing out of Hoover Dam. The amount of water flowing out of a cup has very little potential because there's just not much of it and there's not much of a push. But the amount flowing out of Hoover Dam, well, there's hundreds of feet of water on the other side pushing it out. So therefore, it's got much greater voltage. Watch the well, hold on before you watch the video. The stronger the electric push, the larger the voltage. If you would pause the video right now, go ahead and watch the video that I'll post a link on YouTube. Okay, you should be back. Okay, so next is resistance. Resistance is the measure of how difficult it is for electricity to flow through a material. So resistance is measured in a unit called ohms. Now, think about it this way. Remember the water flowing out of the fire hydrant and the water flowing out of the garden hose? Well, what if it had a lot more push? What if you actually hooked up a garden hose to a fire hydrant? Could the water flow out quite as easily? Of course not. That's because there would be a lot of resistance. You can't fit all that water through such a small hose. Likewise, it's the same with electricity. There is resistance. You can't fit gobs and gobs of electricity through a small hose or through a small wire. If you tried to, you would meet lots and lots of resistance. There's a few different cases for resistance and a few different things that cause resistance, which we'll explore in the next screen. By the way, this is just kind of a fun picture right here. There's all these ohms, and this guy says, "Come meditate with me, man. You don't have to resist everything," and that's kind of a sign for resistance. Well, to use this free screencast software, I can only use 15 minutes at a time. So I am going to upload this video, and then we'll start electricity part 2 in just a little bit, and I'll share that link with you. So thanks for watching. I'll be back in just a bit.